Okay, so let's, with these boundary conditions in mind, now we're going to start just jumping into the Laplace equation. We're going to make some simplifications, and then we're going to start throwing these boundary conditions at the problem until we get an answer. And so we're going to start with our Laplace equation. And we said before that I have this partial derivative of v with respect to x plus a partial derivative of v with respect to y, second derivative for both of those, sorry. And that all equals 0. And so right off the bat, we're going to make a big assumption. We're going to assume that we know, we're not necessarily going to assume we know the answer, but we're going to assume that the answer has a particular form. We're going to assume that v of x and y is going to be equal to the product of two functions. It's going to be a product of x times the function of x, and y, which is a function of y. So what that means is I'm guessing or assuming that whatever answer I get, it's going to have this form where all the x stuff will be in one function and all the y stuff will be in another function, making the variables separate, which is why we call it separation of variables. So I'm assuming that this form works. So for example, I could not have this, if I had something like this, if I had v of x and y equal to like 2x squared plus 9xy plus 4y squared, that would not work with this assumption, right? Because there's no way that I could separate out all the x stuff in one side and all the y stuff on the other side, right? So it could be that it might look like this. It could just be 9xy. That would be fine because maybe 9x is one side and the y is the other side. That would be fine. But when it's kind of mixed together like that, that would not work with this assumption. So we're going to assume that it looks like this. And so now that we've made that assumption, we're going to plug it into Laplace's equation and just see what happens. So we're just going to plug it in and see what we get. So I'm just going to take the x times y, and I'm using capital X and capital Y to refer to the function, the sort of the name of the function, and then little x and little y, those are the variables for those functions, right? So when I plug this in, I now have a partial derivative of x times y with respect to x plus a second partial derivative of x times y with respect to y. So now, when I take a partial derivative of something with respect to x, what do I do with things that have y in it? When you take a partial derivative and I take a derivative, I definitely am taking a derivative with respect to x in this first term. So what do I do with all the y stuff?
You treat them like constants.
Great, absolutely right. We treat it like a constant. So over here in this first term on the left, the x, the capital X, that has all the x stuff in it. So that is going to be doing all the differentiation here. But the y, that's just along for the ride, right? Because y is all contained in that function. And so that means I'm allowed to pull y out as if it was a constant. Because as far as x is concerned, it is a constant. And then the same thing applies in the other direction for the y derivative. The y partial derivative isn't doing anything special there to x. And so I can pull that out. And I get something that looks like this. No magic so far. And so this whole thing still equals 0, right? I haven't changed anything. And so now what I would really like is to make something where I only have x's with x's and y's with y's, because we're trying to separate the variables here. And so to do that, I'm going to divide this entire equation by x times y. Right? So I'm just doing the same thing to both sides, so I'm not doing any illegal moves here. And so when I do that, when I divide by x and y, I'm going to cancel out the y's and I'm going to cancel out the x's, and I'm going to end up with something like this. And then I get 0. And so what is important here is now I have an equation. I'm just going to rearrange it one more time. Yeah, sorry. I'm just going to rearrange it one more time. I'm going to have 1 over x. And now when I rearrange it, whenever you're taking a partial derivative, that means it's a function of more than one variable. But now x is just a function of x. There's no multiple variables here. So this just becomes like a normal, regular, boring derivative. It's not a partial derivative anymore. And I can just bring all the y stuff over to this side. And I get a regular, boring old derivative, second derivative with respect to y. Okay? And so now what we've done, the only thing we've done sort of by ourselves is to make this assumption that it works this way. And by plugging this in and doing a little bit of rearranging, what we end up with is this thing, which is a function of x only, and this guy, which is a function of y only. So what's interesting here is that when you have two functions that are functions of two different variables, what that means is I should be able to change x to be whatever I want, right? If I have a function of x, I plug in a value of x and I get the value out from that function. Same thing with y. I pick a value for y, whatever you want, and then you get a value out, right? I can pick whatever value of x I want and whatever value of y I want. And what this equation is telling me is that no matter what value of x I pick, and no matter what value of y I pick, these two functions are the same, right? The only way this can be true, the only way the left-hand side and the right-hand side can be equal for all x and all y, because again, I could pick whatever value I want for either of them. The only way this can be true is if both sides are constants. Right? And because that makes sense, right? If I pick a different value for x, 2 is still 2, right? If I pick a different value for y, 5 is still 5. And in this case, this equation is telling me that these two sides, they're different functions, but they're both a constant. In fact, they're the same constant because they're equal. Okay. Questions about this kind of maneuver that we've done here? Awesome. Okay, so now that we've done that, what we're going to do is we're just going to pick what we call the separation constant. So basically we have these two functions. They're both equal to a constant. I have no idea what that constant is, so I'm just going to make it up. And so I'm going to pick a value for this constant, and I'm just going to pick whatever I want. I'm going to pick a constant k, lowercase k here. And just because I can, right, k is a constant. I made it up. You could have picked a different letter. I picked k. You could have picked k squared. And you know what? You're right. K squared is a better constant. So we're going to go with k squared. There's nothing wrong with it because I have no idea what k is. Whatever k is, I feel like squaring it. So we're going to square it. If you don't do this, it's not a big deal, but we'll see in a second. I'm sort of thinking ahead. The squaring thing is going to help us out. So what this tells me now is the left-hand side and the right-hand side are both equal to k squared, right? I just sort of picked this at random. Or I should say, I'm picking this arbitrary constant. So at some point later on, we're going to have to solve for k. But for now, we don't know what it is. So now what I end up with is two equations. I have an equation for x that says 1 over capital X times the second derivative of x is equal to k squared. And now I have another completely separate equation for y. That's 1 over y, second derivative of y, and that equals negative k squared. Because remember, we had because we brought that over to the other side, we had that negative sign. Okay? And so to summarize here, the move that we have done here by assuming that we can write the potential this way is we have turned a single partial, a single 2D, I should say, a single 2D partial differential equation into two separate ordinary differential equations. Right? So ordinary just means there's only one variable, right? So the x one only involves x's, the y one only involves y's. Okay?